Okay, so as I said, we want to do it for k classes, and so if you want to do it for k classes, you just sum the variation within class variation of different classes, and you sum of them. So the same as for just two class. Now for k minus 1 directions, you want to minimize trace of W transpose SWW. I said this is a multi-objective, and here is bi-objective optimization. And simultaneously, you want to maximize trace of WS between class variation. And now your Lagrangian is a matrix, such an interesting object. It's now a matrix, and trace of omega transpose SBW minus lambda, trace of W transpose S within class W. And same as for two class, we can just generalize it for k minus 1 classes, and this is the weight. I said it is weight, and your lambda is the diagonal of all eigenvalues. And now each vector of W is SB is not rank 1 anymore, so you have no problem. So solution is the eigenvector of SW minus 1 SW. So SW is easy because easy to obtain. Let's say SW is easy to obtain, is easy because you just sum the covariances. But between class covariance is hard to compute. So the trick is to use, so I use a trick. The trick is that we know the total variation. We know the total variation. And so it is between class variation and within class variation. So simply I can find SB because SB is S of total minus S of within class. S of total, I thought I know it because it is just 1 over n xi minus mu. It's just for all of them. And for LDA, feature discriminant analysis, we have assumed that we can find there is just one covariance, although the means of classes are different, but you assume that you only have one covariance. This is the basic assumption of LDA, so no problem. Now we are ready to shift to Wasserstein Metric, because in order to understand Wasserstein discriminant analysis, of course it is the generalization of linear discriminant analysis, but you need to know something, some basic thing. What is Wasserstein Metric? So we want to define a metric on space of probability distributions. It's not in a simple object because you are working on the space of functions, which is different than space of just Rn or Rd. It's infinite dimensional approach. So you need infinite dimensional tools. So it's not finite anymore. It's infinite dimensional. Linear algebra, for example, what you see, you can have a matrix, n by n matrix. It is finite. But the space of functions are infinite dimensional. So you need to know the distance between those functions. One of the good functions are probability distributions like mu and v. So like in Euclidean, you define the distant Euclidean norm. So for example, in 2 dimensions, you define the distance between A and B. These are A and B points in Rn. Here are 2. But here in infinite dimensional, your points are, each of them are a function. For example, this is mu, this is nu, all of them are function. And one of the good functions are, as I said, those are probability distributions. They're good functions. And so we want to now find, like Euclidean, that you find the metric is, the distance between them. In infinite dimensional, a natural metric between probability distributions is minimize expectation of x variable, it's a random variable, and y. So for all x in x and all of y in y, for example, x in linear discriminant analysis, you want to know what is the variation between 2 points. This is from class 1 and this is from class 0. You want to know the variation. For example, this is class plus, this is class minus. So this is the Wasserstein approach. So you minimize the expectation. So you want to find, and the law of x is just mu. It's a probability distribution. In measure theory, we usually use mu and nu, these Greek alphabets. And because, in practice, you don't know that. So, we do empirically, we estimate them in statistics and in practice. So we estimate them. So these ideas are from Gaspard Monge, is a great French mathematician in 18th century. And also Kantorovich in 20th century for modern formulation. And of course, nowadays I like Cédric Villani, a great French mathematician, Fields medalist in 2010. He's now a politician as well. A very nice person, it's very interesting why he was interested in optimal transport, geometry, PDE, and all those things. You should watch his lectures in YouTube to see how you can connect different fields of mathematics. And so it is a creativity that this man has. And so let's say an example of what is optimal transport. For example, you want to, all these things about optimal transport, that you want to somehow put a mass here and put it here in an optimal way, which is you reduce the cost of doing that, and you can formulate this optimal transport problem by saying that, okay, you want to minimize this t. So this t map, this transformation map, for each point here, we have a point here. So we want to minimize the distance between x and t of x, and then your measure. So subject to, of course, your t must push forward the mu. So we say t push forward mu is equal to nu. So t must push forward the mu measure towards nu. From mu, measure mu, towards measure nu. This distribution and another distribution. So this push forward to nu. So you can use any cost function in, for example, Monge in 81 said that you can use any cost function. Okay, so it's not necessarily a distance. It could be any cost function. Distance is just an example of a cost function. But for practical and some useful properties of a matrix, let's say this cost function is defined as a distance, a metric. So now we are talking about the Kontrovich works and definition. The Wasserstein distance between mu and nu in this probability distribution space is that you can define the Wasserstein distance between probability distribution mu and nu. So it's by definition, it's infimum of d of xy, p of d of x, d of y, 1 over p. And just to say the dual of that is very interesting and has good properties, especially in the regularization that some people write articles about that. It's interesting that the dual of this problem is just supremum over all functions phi that are just one Lipschitz of constant 1. So it's supremum of phi d mu minus d nu. So let's say an example. You have two sensors, or let's say in machine learning you have two classes. You know, MNIST dataset, all of these datasets, you want to classify benchmarks. So sometimes man and woman, sometimes in activity, for example, datasets, if you are a data scientist, fighting, not fighting, you want to classify your images. And so in those things, if you just want to do a linear interpolation of your distributions, just linear interpolations, what happens? In linear interpolation, what you are doing is just, you cannot move too much. It's like this. This is just linear interpolation. But in Wasserstein, when you want to say what is the difference between two distributions, and you want to find the linear interpolation, you achieve something like this. It's like it is moving. So this is more natural because, for example, it is an infinite dimensional. Of course, you cannot imagine because each point is a function. You are moving from this to this function g to this function f, from this point to this point, and so you can do it. You can go through that in a very natural way. That's why some measures of in probability distributions, such as Kullback-Leibler divergence, these are not, for example, Kullback-Leibler, because it uses the division, and so it's not natural. But this object is more useful because it's the difference of two objects. So it's a good measure of the difference of two probability distributions. And that's why Kullback-Leibler divergence and other, not Brakman divergence, other divergences are not good. In the sense of it is not natural, but Wasserstein Metric is very natural. That's why mathematicians like that. And of course, it has many applications. In GANs, we have two great things in deep neural networks. One of them is autoencoders, different variation, of course, of autoencoders, variational autoencoders, and those things. But GANs is generative adversarial neural networks. And you have a latent space, which is a very low dimension, and you want to transform it to a very high dimensional space. So your goal is to minimize WP, Wasserstein distance of V of data, and you're transformed, so push forward of theta mu, and you want to minimize this. So you see that even you can use it in GANs as well. Another application is distributionally robust. And those things, and by Esfahani, which is an Iranian mathematician, and I like that. And so you can use Wasserstein distance in different problems, different framework. But what is the reality? Reality is that you don't know all of these things. All you have is just IID, identically independent samples, like statisticians, x1 to xn, and it is drawn from mu y, and also y1 ym is drawn from nu. So for example, this is from class A, this is for class B, and you just calculate the mean of them empirically, just empirically. So in practice, you only have these empirical things. So the problem is how to compute or approximate Wasserstein distance between the estimated distributions, because you don't have the actual distributions. So you want to. So this is a problem one, and problem two that statisticians are very interested in is that you want to know how far, how close that they can be when you increase your sample size. Can you just reduce these? Can you just converge the Wasserstein distance of this, which is the actual things, to your approximations? Wasserstein of, in other words, I can say that are your empirical approximations good enough so that in order to say that the distance between them is as low as possible. So this is a function of n and m, where n is sample size of class A, m is sample size of class B, and so we define mxy. I will define it again in a context of generalization of linear discriminant analysis. But for now, let's say it's just the distance. Because now you don't have continuous thing, you have discrete things. So you are discretizing that integral that I've just mentioned. And so that's why everything is just points and matrix. So it's discrete. So by definition, U is all P, all matrices in, of course, positive quadrant, because probability is positive, and you multiply by one vector, it becomes A, and P transpose N becomes B. So the optimal transport problem